Okay, welcome to lesson 37. So we were looking at Z procedures for a single proportion from one population. Now we might have more than one. Specifically, we're going to focus on two. So maybe I have two populations or two groups that I want to compare the proportions to. Maybe I want to know the proportion of defective parts, of parts that are defective for machine 1 versus maybe a newer machine, that kind of idea. So we're going to go ahead, look at two-way tables and side-by-side bar charts, because remember, if we're looking at proportions, it's a categorical variable. Bar charts or bar plots should be our go-to. And then we're going to talk about the sampling distribution for difference in proportions there. So the example we're going to use for our two sample proportion problems, we went ahead, there's a survey from a magazine article, and they were really interested in Americans that believed in extraterrestrial life, so life outside of Earth. So they went ahead, they took a survey of 100 randomly selected Americans that are not college educated versus 100 Americans that are college educated. And from there they said, okay, well, 35 of the 100 non-college educated Americans believe that there's life outside of Earth. 47 of the college educated Americans believe there's life outside of Earth. They want to more formally compare these proportions. So we have a side-by-side bar chart here. So these first two, they go with the non-college educated folks. So 35 looks like counts here. 35 of the 100 didn't believe in extraterrestrial life. 65 did not. Here's the college. 47 believed. 53 didn't. Things to note is we have a sample of 100 for both groups. So count makes sense, but if you had very different sample sizes, you would probably want to have proportions on your y-axis. Otherwise, it gets really goofy looking really fast because sometimes the bars are so much higher for one group than the other. It is really misleading. Okay, so the sampling distribution of p hat 1 minus p hat 2. So we can actually look at the difference of the sample proportions. So I can go ahead, repeatedly sample from population 1, take a sample proportion, repeatedly sample from sample 2, take a sample proportion, take that difference, and then repeat the process over and over. And I will end up getting a distribution that, what do you know, has this beautiful bell shape. Right? I mean, you're probably going, okay, come on, like really? But if we take big enough samples, and we'll talk about the big enough again, the central limit theorem saves us. It saves our butts. It tells us, hey, we know that the sampling distribution of p hat 1 minus p hat 2 is going to be roughly normal. It's going to be centered at the actual value of p1 minus p2, so whatever the difference in proportions really is between the populations, with a standard deviation of, and that is a little bit longer than it was before. So definitely strongly recommend having this written out somewhere. But if you notice, this is like if I were just looking at the standard deviation of the first sampling distribution. This is the sampling distribution just for the second. Add them together under the square root. By no means are we sitting here going, oh, we want you all to memorize all these equations. It definitely helps to write them out. So we're going to start with a confidence interval. The next lesson, we'll go ahead and do a hypothesis test. But we use a two-proportion Z confidence interval for a difference in proportions when we want to estimate what the difference is between two proportions, so between P1 and P2 from two independent populations. So the parameter of interest is P1 minus P2. That's what we're interested in getting at. So now that we have two samples, both samples need to be random and representative. I'm going to stick in here independent populations. Oops, I can spell sometimes. So the idea is individuals in sample 1 could not possibly be in sample 2 because you have independent populations. You want representative samples always. And then we need to know that our sample sizes, N1 and N2, are both going to be big enough that we can count on the central limit theorem kicking in. So specifically for the sampling distribution of p hat 1 minus p hat 2, it's going to be roughly normal. So for specifically, it means for confidence intervals, the number of successes and the number of failures in both samples is at least 10. So you took a big enough sample that you guaranteed you saw 10 of each in each sample. And a big part of this is there are things that are not very prevalent. So even looking at, there was an article written recently that they're looking at the TRACE project for COVID-19 here in Corvallis, and they're like, oh, well, we're seeing about 2 in 1,000 individuals are testing positive here. Well, that prevalence is so low. You want to make sure that you take a big enough sample size to get at least 10. So it's absolutely, you want to make sure that you're not taking, oh, if it only happens, to 2 in 1,000 people, well, guess what? If you only take a sample of, 1,000 people, you would expect 2, right? So that's not going to be big enough. So you want to make sure you take big enough samples to see at least 10 of each in your samples. So then the confidence interval for so it's our point estimate is going to be the difference in proportions. So things to note is if you write P1 minus P2 and P hat 1 minus P hat 2, this is okay, but then you need to say, oh, 1 is equal to whatever 1 is, I don't know, college, educated. 2 is equal to non-college. Just know that what R does by default, it does alphanumeric categories. So if you had college and non-college as your names, it would make college your first category and non-college as your second. Z-star, it's going to be the same as it's been. We're going to usually go between 90%, 95%, and 99% confidence. Those same 3 Z-star values. And then our standard error. So it's going to be a little bit, definitely putting in a calculator can be a little rough. R probably is an easier way. We did provide some R code that does this calculation here for us. So our best way of estimating P1 times 1 minus P1 over N1 plus P2, 1 minus P2 over N2. Our best estimate is going to, if we're doing a confidence interval, is going to be using P1 hat and P2 hat. We'll just plug that in right there. Okay, so back to our extraterrestrial example, right? And I wish this didn't make me think of that Katy Perry song. Oh, that's sad. So we are interested in the difference in proportion of non-college educated Americans that believe in extraterrestrial life and college educated Americans that believe in extraterrestrial life. I can almost guarantee you exactly why. Oh, okay. So I'm going to label college as 1 and no college as 2. For the very basic reason that when I subtract, I like to have a positive p hat or difference in p hats. You absolutely do not have to. You will get the same interval but opposite signs. So my question of interest, what is the difference in proportion of college-educated Americans and non-college educated Americans that believe in extraterrestrial life? So I need to specify, so college minus non-college. Because if you say difference, you need to say what order you're subtracting in every time. Super important. So then here, say I did college, no college. I'm going to even call it PC minus PNC. So proportion of all college educated folks that believe in extraterrestrial life minus the proportion of all non-college educated Americans that believe in extraterrestrial life. So specifically the difference in proportion of people that believe in extraterrestrial life between college educated and non-college educated, and I specify my order. It is incredibly important. Every time you will lose at least 1 point if you don't specify the order. If it's not obvious, like which one you're subtracting from the other, it will be a point every time. So then our conditions. So I'm going to throw in the independent. Yes. I'm assuming that in order to be a college-educated person, you can't be a non-college-educated person and vice versa. I'm assuming they're probably using something like a bachelor's degree to define it, but it's one or the other. You have a degree or you don't have a degree. The people they're sampling from can't be in both. So yes, I would say yes, they're independent. Not only that, they took a random sample of 100 college-educated folks and a random sample of non-college-educated folks. Probably self-reported. That might be problematic. So then the condition that takes the most checking is, hey, did we have at least 10 successes and 10 failures in each? So here I'm defining the success as believing in extraterrestrial life. So in the no college group, I had 35 out of 100 say, so I'm going to say non-college. So 35 and 65. So 35 believe in it, 65 didn't. Both of those are at least 10. That's good. If I look at college, I had 47 folks that believed in extraterrestrial life, which means I had 53 that didn't. Both of those are at least 10. So yes, I meet the size condition. Both of my samples are big enough. My confidence level, it's a 90% confidence interval. So that means I'm going to use a Z-star critical value, which that's just going to be 1.645. So I've got that there. Inventory. I'm going to put inventory on the next slide. There's really not enough room in here to write it. So things to note. So my inventory, so P hat, remember I said 1 and 2, that's how we have it. So P hat 1 was equal to 0.47, P hat 2 is equal to 0.35, N1 and N2 are equal to each other, they're both equal to 100. You can totally write them separately, that's cool. And then P hat 1 minus P hat 2, because that's the order I have here, 0.47 minus 0.35, 0.12. So what this is oops, I'm sorry. This is my point estimate. The difference in sample proportions that I actually observed in my samples was 0.12. So there was a higher proportion, it's positive 0.12. There was a higher proportion of folks that believed in extraterrestrial life in the college group. That's what I'm getting from this being positive, because I had college folks minus non-college folks. So a positive number means it was higher for college folks. And then also my Z-star, that's 1.645. So yeah, it's a little cluttered in here, but I now have everything I need to plug in. So I'm going to say, okay, well, that 0.47 minus 0.35 plus or minus 1.645 times, and this is the part I usually will throw this into R. It's very, very easy to goof up. So 0.47 times 1 minus that. Oh, thank goodness the denominators are the same. It actually makes life so much easier. 0.35 times 0.65, because that's 1 minus that, over 100. Seriously, it is so much easier when the sample sizes are the same. Ideally, we do have equal sample sizes, but human beings in particular are infamous for dropping out of studies. Just saying. So a lot of times we don't get them. So 0.12 is my point estimate, plus or minus. I'm going to take it out to about 4 places. 1, 1, 3, 6. So then I get 0.0064, and that's positive, to 0.2336. So a couple of things to note. Both of these are positive. 0 is not in there. In fact, this entire interval is above 0. This kind of implies that the first group, so the college group, has a higher proportion of folks that believe in extraterrestrial life than the second group, at least based on this study here. Further, I just want to make a comment, is the lowest, so CI for P, actually, CI for P, the lowest it can go is 0, the highest it can go is 1. I'm just gonna, there's no real difference here, right? For us. So the highest confidence interval for one proportion can go is 0. The lowest it can go there is 1. If I want to do a confidence interval for P1 minus P2, the lowest it can go is -1, and the highest it can go is +1. So keep that in mind. You can get negative values. If you get negative values, it just implies that the proportion was smaller for the first group than the second. But if you go further out, like lower than -1 or higher than +1, something's gone sideways, you need to cap them off. So just a note. So now we need to write it up. So you might notice it's a little more complicated now. I tried to go ahead and include a template. I really can't emphasize enough, like, getting really comfortable with these templates really is very useful here. So 0.0064, we're very formulaic with the things we like. So both of these are positive. My point estimate was 0.12, that was also positive. So with 90% confidence, the true proportion of, so my first population, so college-educated Americans, I don't know what age group, that would probably matter. Or the year, because honestly, if you took this, 50 years ago, it'd be different. So the true proportion of college-educated Americans that, that believe in extraterrestrial life, and this is the part I regret writing by hand every time, terrestrial life, is estimated to be, so because I did P1 minus P2, that was specifically P college minus P non-college. I talk about college and then I talk about non-college. Is estimated to be between 0.0064, and it's positive, so higher, and 0.2336, that's also positive, higher, then the true proportion of, so now I'm going to repeat this for a second, so non-college educated Americans that believe in extraterrestrial life. Oops. Extraterrestrial. Don't mind me just dropping stuff. Life with a point estimate of So what I actually saw, the difference in proportions in my samples, 0.12 higher for the college group, higher. So with 90% confidence, the true proportion of college-educated Americans that believe in extraterrestrial life, so I have my population and my variable of interest right there, is estimated to be between, on average, 0.0064 higher, because that endpoint is positive, and that's why the higher, and 0.2336 higher than the true proportion of non-college educated Americans that believe in extraterrestrial life. With a point estimate, so this is p hat 1 minus p hat 2 from samples, higher, because that's also positive. So that would be our right up there. And I believe, yep, sure enough, our next step is going to be doing a hypothesis test for a difference in proportions. So we'll see you in a few.